We're Team Zeta Cubed. I'm the team manager, Alex Blakely, and I'm also in charge of budgeting and design.
I'm Austin Piper. I was in charge of the timeline, some of the design, some programming, and the fluid mechanics.
And my name is Finley Butler. I was also working on the design and the mechatronics analysis.
Our faculty advisor is Dr. Sean Dwan, and our industry contact from the Intel Corporation was Dr. Ralph Jensen. So our project was provided by Intel down in Oregon, and they basically needed a solution to help opening all their massive numbers of servers quickly, easily, and safely to facilitate daily maintenance. And some of the stipulations they had is they wanted to be spring-loaded, self-opening, and they want to be in some form of a hinge, and they want to be able to, when it closes, protect the server components from slamming. So a damping component was also needed. And during a preliminary review, the main issue they were having is that the products were either too small to fit inside the servers or they're way too expensive.
We were actually unable to go to Intel for a site visit due to COVID, but this is our design server. We actually made a visit to the IT department at St. Martin's University, and we're able to get a little tour of their server room. We're opting to work with the Dell PowerEdge 2950. And here's our torque hinge design after consolidating our preliminary CAD designs. Off of that design server, here are some door specifications. And the door, we had to calculate a moment arm to figure out the load that the springs have to undergo, and basically the torque of the springs has to overcome the maximum door moment to achieve a good torque hinge. And we're using the technical guide from Dell to get some of our design variables in there. Here are the moment arm calculations. We actually opted to open the door from the side just to achieve a lesser moment arm and to possibly get a smaller hinge design in there, but we could also include extra hinges and open it from the back. But these are very realistic moment arm calculations to distribute over the number of hinges.
For our initial spring design, our plan was to use 2 springs, hoping to overcome the moment. And we had to make a few initial design values that's shown in the chart. And from those design values, we were able to calculate our wire diameter and our outer diameter, all the geometry. We were able to calculate the expected stress from our door on the spring. And when we end up attempting to calculate the design geometry for the spring, it ends up having a number of coils of 0.002 and an inner diameter of negative 2.95 millimeters, which is impossible. So we continued to try and find a different spring material that would meet our needs. However, we were not able to find the design stress values to custom make a spring.
So for the rod design, we needed it to be small enough for the springs when they move to actually clamp down on it. And so basically what we had to do was first plot out the kind of forces that would be acting on there, and we thought it'd be mainly shearing forces going downward, which is shown in the bottom left photo. And then we chose our material, which is the SAE 1020HR hot rolled steel, and it had an ultimate tensile strength of 79 megapascals, and so we used that to find the actual endurance limit, and then we divided that endurance limit by a design factor of 4. Which 4 is generally used as a for more ductile materials, which would be including with this. And it actually was a little bit of an overkill as far as the type of material. Steel is very strong, so it wouldn't even be close to failing. And so we would be able to probably, which we probably will, downgrade it to either an aluminum or some kind of other thing we can actually 3D print off. And then this is what our final assembly looked like when we put together. So on the left was our final CAD designs, and then when we put it all together, that's it on the right. And then this is our final production drawing, and it got a little crowded in there, so I put the springs and separated out them all separately so you could see everything. And the maximum diameter we have on the outside, as the hinge, as you can see right there, is 13.6 millimeters, and so you can tell it's very small inside the server. And so these are some of the codes and standards that we're following to make sure that what we're planning out actually can be replicated and comes out exactly the way we want it to in the end. So first, we decided to use the metric system. In general, it's just the easiest for us. It's what most of our education has been geared towards, is using the metric system. And then ISO 9000, which was basically a way to do quality assurance. And we have to pay a lot for it. So we're actually using one of the classes me and Austin are taking, new product development, where we go through various steps, and a couple of them are design verification and validation, and those focus on certain steps that make sure that, like I said, what you start with and your goals are met like throughout by checking every step of the way as you go to the end.
The other codes and standards we use are the BICSI 002, and that was standards based on how a server room should be set up, all the rules and regulations of what can be in a server room. And as well with our spring, the spring is built to ASTM standards. That's from the company. That's a standard that will always be used.
Some major roadblocks and risks involved. The spring's actually way more expensive than we initially predicted, and so figuring out how to buy those in bulk to drive the cost of the springs down. Another big roadblock was not being able to do that site visit, but we're getting around that using a different server and making some assumptions on our own and just using our industry contact. We have no financial backing from Intel, and so all of our resources are being allocated from St. Martin's and their money, and there's an extreme lack of space inside the server, so figuring out how to get the size constraints down of the spring in our design calculations has been difficult. And the server door also shifts back when opened, and so figuring out how to install the hinge there is going to be another roadblock for us.
For our timeline, this timeline provides the real dates we've accomplished things up until December 1st of 2021. Our plan is to now order parts and start working towards a prototype. The bolded dates on our timeline are required dates for our senior design class, and we project that we'll be purchasing parts and ordering parts by the end of next week.
So this is our basic budget. The top right one is basically what we thought at the beginning of our semester for starting, and the bottom right is what we have ended up allocating so far. And we're pretty much on track. We thought about 40% would be raw materials. It's actually less than that so far. And we set aside a little bit amount of petty cash just in case for emergencies and as a little bit of a cushion. And using this, as far as materials so far, we're under budget right now. So.
Some next steps heading forward are going to be exploring potential materials in our spring design, and we're really looking into doing some 3D printing, and so using products or materials such as nylon, definite possibility, and to drive some of those design calculations down with their strength and lightweight characteristics. Also applying computer-aided analysis to our designs and finding some weak points and confirming that our design is